This is Raymond Lam from the Department of Biomedical Engineering in the City University of Hong Kong. I'd like to introduce a couple projects we've developed over the past year on the theme gel-less electrophysiological detection systems. The core technology is on how to measure the biopotentials. Biopotentials are electrical signals or voltages that are generated by physiological processes of the nervous, muscular, or glandular systems in the human body. Back in the old days, this is a groundbreaking discovery actually. Dodgkin and Huxley received the Nobel Prize for Physiology or Medicine in 1963 for their discovery. We were interested in the electrical spikes, which are measured and have diagnostic importance in electrocardiography, in short ECG, electroencephalography, EEG, electromyography, and so on. Let's take the left figure for example. If we mount multiple biopotential electrodes at different locations on the human body, so on the limbs or on the chest, in different orientation across the heart, then we will be able to detect sort of the spikes of the heart in different orientations. And this is the basic working principle of ECG. Likewise, if we mount the electrodes over the head in different orientation across the human brain, as shown in the right figure, then in this case, we would be able to monitor the brain activities. So this is the working principle of EEG. Currently, these ECG or EEG systems are functioning very well, but they are not very user-friendly. The major reason is that we need to apply the gel between the human skin and the electrode, and we need to clean that up afterward. So it's quite messy sometimes. Years ago, we've developed a technology to achieve the gel-less and stretchable biopotential electrodes. This technology is developed under the support of the Innovative and Technology Fund. It also obtains the US patent. So these electrodes are made of a polymer, a conductive polymer, highly biocompatible, and is deformable and flexible so that it can attach on the human skin. On top of these, we've made the electrode embedded with some microstructures so that it's consistent in terms of the conductivity or even impedance along a particular direction under stretch. So it's no longer sensitive to stretching. It provides a unique advantage to maintain the consistent sensitivity of the sensor. As shown in the upper left corner, the geometry of the electrode is basically two layers of thin membrane sandwiching an array of cylindrical pillars. Now, if we stretch the entire polymeric electrode, then we have simulated the deformation of each of the pillars as shown in the right simulation results. Under stretch, the strain would be developed over the upper and lower layer, but not on each of the cylindrical structure. These pillars dominate the electrical conductivity. In short, with such a structure including an array of cylindrical pillars, the conductivity can maintain to a very consistent level, almost independent of the stretching level. As plotted at the lower left corner, we can see that even though we stretch the membrane in an experiment, the conductivity of the entire structure is consistent. Using the gel-less and stretchable biopotential electrodes, we've developed an ambulatory ECG monitoring systems. So it includes a few key components. Those electrodes are embedded inside a jacket or a vest, and the user or patient would wear that with also an ECG electrical circuit. So it's placed inside an ECG box. This circuit continuously sends out the ECG signals. On the other hand, we have a computer connected with the corresponding Bluetooth receiver. And we've developed also a graphic user interface to store and plot these ECG signals in real time with certain level of real-time data analysis as well. Similarly, we apply the gelless and stretchable electrodes to develop an ambulatory EEG monitoring system. This EEG monitoring system was invented under another innovative and technology fund, and is a collaboration with the medical doctor of Prince of Wales Hospital. So in this case, we manufacture an EEG head with multiple electrodes inside. The EEG head contains circuitry, and it sends the EEG signals to outside in real time. On the other hand, we developed a mobile phone app to receive those EEG signals. At the same time, this mobile phone can use its camera to monitor the patient's movements. This app would also upload the EEG data as well as the recorded video to a server, which is expected to be installed in a hospital so that doctor can check or monitor the patient in real time. One application of the EEG monitoring system is for the discovery of epilepsy. And here we see an example of the EEG signals. It captures the onset of seizure, which is a very early stage of the epilepsy. These projects have been reported by different public media, for example, the TV news, magazines, and newspapers. Thank you for watching.